We're going to wrap up Chapter 6 looking at some applications of integration with physics. And we're going to talk about work and fluid forces in this section. We're going to start out looking at work. Some of these formulas might be familiar to you if you've taken physics in the recent past. The first one is the work formula if it's a constant force. It says when an object moves a distance d along a straight line as a result of being acted on by a force of constant magnitude F in the direction of motion, we define work done by the force as work equals force times distance. In the metric system, the unit for work is the joule, which is the Newton meter. In the metric system, and you may or may not remember this, the Newton is a unit of weight. In the British system, the unit of work is the foot-pound. Okay, so again, pound is the weight that we use. Now we can take this formula and apply it to variable forces. So I've got a definition here. It says the work done by a variable force in moving an object along the x-axis from x equals a to x equals b is the integral from a to b of f of x dx. And we're going to look at that formula and apply it in a couple different ways in this section. But I first want to give you one more thing. This is Hooke's law. And Hooke's law has to do with a spring and stretching or compressing a spring. It says, Hooke's law says the force required to hold a stretched or compressed spring x units from its natural or unstressed length is going to always be proportional to that distance x. So the force is going to equal some constant k times x. That constant k is called the force constant or the spring constant, and it's going to be measured in force units per unit length. So it will either be in newtons over meters, or it will be in pounds over feet. The first example I'm going to work through says a force of 2 newtons will stretch a rubber band 2 centimeters or 2/100ths of a meter, and I'm going to actually use that second version of the length. Assuming that Hooke's law applies, how far will a 4 Newton force stretch the rubber band? And I'm going to pause here and answer that first part before I come back to the second part of this question. So how far is this 4 Newton force going to stretch the rubber band? Well, using Hooke's law, force is this constant k times x, where x is how far it's being stretched here. So to find k, I'm going to use the first part of what we're given, this 2 Newton force, so the F is 2 newtons. We're looking for the constant k, and it's being stretched 0.02 or 2/100ths of a meter. To find k, we're just going to divide 2 by that 0.02. So k is equal to 100 newtons over meters. So now we have a value for k, so we can put it into that Hooke's law formula. So in this case, F is equal to 100 times x. So to answer that first question, how far will a 4 Newton force stretch that rubber band? If I put 4 in for F, and then solve the equation for x, so just simply divide 4 by 100, x is going to be 0.04 meters, so 4/100ths of a meter. So that answers the first part. The second question, how much work does it take to stretch the rubber band that far? Well, I've got it off screen right now, but let me scroll down to bring it back. We're going to use this integral formula. So in this case, we're stretching the rubber band up to 4/100ths of a meter. So we're going to go from 0 to 0.04. We already know that force is 100 times x, where x is the length that it's being stretched, and then r dx. So it's just very simple here to integrate. The 100 can get pulled in front. When we integrate the x, it's just x squared over 2. And we're going to evaluate that from 0 to 0.04. So you can see the 100 times the x squared over 2, that 2 can cancel into the 100, so we just have 50 times x squared. Start out by plugging in the 0.04 for x, so it's going to be 50 times 0.04 squared, minus plugging in the 0, 0 squared is still 0. If you multiply out 0.04, you're going to get 0.0016. Obviously that minus 0 doesn't do anything. And then multiplying 50 times that 0.0016, we're going to get 0.08 joules. I use joules, which is Newton meters, because we're dealing with the metric system here.